Hi everyone, we're going to continue on with chapter 10. So we'll be finishing up chapter 10 today. When we are done with chapter 10, we actually won't have a quiz right after. We're going to combine chapter 10 and chapter 11, and that quiz won't be due until May 15th. So last time we were talking about different Grignard reagents and organolithium reagents with the reaction of different carbonyl groups. So epoxides, ketones, we looked at formaldehyde, we looked at a aldehyde in general. So when we're looking at Grignard and organolithium, we have to think about these again as strong bases, so they're strong nucleophiles. So besides their addition to carbonyl compounds, they actually can react with other acidic or electrophilic compounds. So if we look at the Grignard reagent shown here, or it could be organolithium, so something like this, and we react it with an alcohol, for example. So we'll have a carbonyl here, we have our alcohol here. What actually would form would be something like this plus this group here. So this hydrogen here, we know from earlier chapters, this is going to be our acidic proton. So what you'll notice when you're looking at the products is that we actually have no carbonyl addition. So this is really common when you have the presence of a protic compound, such as alcohols. So we know as OH, this would be our acidic proton. Amines, so when we're looking at an amine, we have this acidic proton. And then when we're looking at carboxylic acids, so carboxylic acid, remember, is going to be this. So again, this proton right here. So again, when we're using these strong base Grignard reagents or organolithium reagents, they will work well with aldehydes, they will work with ketones, they will work with epoxides. But when we have acidic protons, something like an alcohol, an amine, or carboxylic acid, it generally is just not compatible. So they're not typically used when we have, again, those types of functional groups on a compound. So the next type of reaction that we're going to look at is going to be Gilman reagent. So a Gilman reagent typically is shown like this. So R groups can be anything. It can be a phenyl ring, it could be just a methyl group, an ethyl group. So why these are used, I should mention too, these are also mentioned or called lithium dialkyl cuprates a lot. So again, you can hear all different terms for these. They all do the same thing. So why these are useful. So if you want to couple two R groups together efficiently, we can do it by using this organocopper reagent. So this again would be your organocopper reagent. So again, our Gilman is shown like this. So what actually happens is we're going to have lithium plus charge, we have our copper as a minus charge, and then you would add some alkyl halide to it, and we would have coupling of our two groups. So we would call one of these R prime. So you're taking one of these groups and you're coupling it with your chain on that alkyl halide. So when we look at the formation of a Gilman reagent, so if we have something like this, so we have two equivalents of this alkyl bromide, and then we have 4 equivalents of lithium in hexane. So this should kind of ring a bell. This is how we would make our organolithium reagent. This would give us 2 equivalents of this organolithium reagent. Then what we're going to do is we would add copper iodide to the solution, copper 1 iodide, and we would form, so we'd have CH3, CH2, 2, and then copper lithium. So this right here would be our Gilman reagent. When we take that Gilman reagent and we react it with our alkyl bromide or alkyl halide, it can be bromine, chlorine, iodide, all of these halides will work. So what we have, if you think of this, we have copper minus lithium plus, and then we have a CH2, CH3 coming off this, another CH2, CH3 coming off of it. So what we would end up with is going to be this product right here. So when we look at it as, let's look at it as, you don't need to know the actual mechanism for this, but I'll show you it as like a simplified mechanism. So what happens is one of these R groups on the organocopper reagent is going to come in and attack this carbon here. As it attacks this carbon, the bromine CBr bond or C halide bond will be breaking. So again, we have, if we look at carbons 1, 2, 3, 4, we have 1, 2, 3, 4, and then we would have 5, 6. So 5, 6. And then this we'll call like 2 star. So this is coming off of our carbon 2. So again, I think it's really, really useful to number carbons when you're either coupling it or really when we looked at oxidation or when we're going to be looking at reduction. So it really does help to number your carbons so you kind of know what you're working with a little bit better. So we have talked about different oxidation reactions. So we skipped potassium permanganate, but remember we looked at ozone. Now what we're going to look at is we're going to look at reduction. So let's look at reduction of carbonyls with hydride reagents. You may see hydride just written as like H minus a lot of times. So a hydride reagent adds a H minus and it's going to reduce that carbonyl to an alkoxide ion. And then we can protonate that and give us a alcohol. So the mechanism isn't really necessary for these reactions. You don't have to know that, but we're going to talk about a couple different types of reducing agents. So the first reducing agent, which should look familiar to you, is going to be sodium borohydride. So when we look at sodium borohydride, this is going to be a mild reducing agent. So that's important to know. So what this means is when it's a mild reducing agent, what it's going to do is it can reduce aldehydes. So remember, this would be an aldehyde, and it can reduce ketones. However, it cannot reduce esters. So something like this would be an ester, or carboxylic acids. So again, it can sodium borohydride can reduce either an aldehyde or a ketone, but it cannot reduce a carboxylic acid or an ester. So when we look at the structure of sodium borohydride, we have, so we're going to have sodium plus, so the boron hydrogen bonds are going to be polarized with that partial negative on the hydrogen. So again, sodium borohydride is just going to be effectively a source of that hydride. So a lot of times this is just going to be shown as H minus. And again, remember that this one is going to be a mild reducing agent. When we look at some examples, so if we have this compound here, so looking at this, we're going to say, okay, we know that this is a ketone, right? Because we have the general formula like this. So we know that sodium borohydride could reduce this. Typically, methanol is the solvent that's used for these types of reactions. So let's number our carbons, 1, 2, 3, 4. So we're going to keep the same number of carbons, 1, 2, 3, 4. But this carbonyl group on carbon 2 is now going to be turned into an alcohol. I'll show you kind of what's happening here, just in case the mechanisms help you, but you wouldn't be asked to show the mechanism here. So hydrogen's going to go in this position, the electrons are going to go to oxygen, and then what would happen is we are going to have, so 1, 2, 3, 4, we're going to have O minus, and then we have our solvent, and this can kind of take the proton from our solvent, and that would give us this product right here. Let's look at another example with sodium borohydride. So if we have something like this right here, so functional groups again are going to be very important. So we have sodium borohydride, again we'll do it in methanol. So looking at this group right here. This is going to be an ester. And then we have this group right here. This is going to be an aldehyde. So again, because sodium borohydride is mild, we know that a mild reducing agent, we know that we cannot reduce the ester. So let's number our carbons. So we have 1, 2, 3. So we're going to have our 1. So we have our oxygen here and our methyl group there. That's not going to change. Then we're going to have 1, 2, 3. So off of, did I miss one? So we have 1. Oh, sorry. It'd help if I could count. So sorry about that. 1, 2, 3, 4. 1, 2, 3, 4. So off of carbon 4, we can reduce that aldehyde. So that means we're going to have an OH coming off of that aldehyde. So again, this ester right here, we cannot reduce to a alcohol because sodium borohydride just isn't a strong enough reducing agent. So remember, esters and carboxylic acids are not affected in the presence of sodium borohydride. So if we look at another reduction, so let's look at reduction with lithium, aluminum hydride. So really it's going to be the same idea, except the only difference is that lithium aluminum hydride, this is going to be a strong reducing agent. So since it's a strong reducing agent, it can reduce more functional groups. So again, it's going to react in much of the same way as the sodium borohydride. It's just going to be a much stronger reducing agent. So it's going to basically unselectively reduce all the carbonyls that you have in a certain compound. So that means it can do carboxylic acids, it can do esters, it can do ketones, it can do aldehydes, it doesn't matter. So it will reduce all of these different functional groups, unlike sodium borohydride, who cannot do carboxylic acids or esters. So let's look, so if we look at the structure of lithium aluminum hydride, so it's really the same idea. Our lithium is going to be our plus charge, and then our minus charge is going to be over here. So it's going to look mostly like this, just H minus it's typically shown as, and again, this is going to be strong. So when we look at our example, we have something, let's look at this one again. Maybe I can count better this time. So we have 1, 2, 3, 4. So again, we have to think about the groups we have. We have ester, and we have aldehyde. So same idea, we're going to number carbons. So this would be like 1 star because it's coming off the one group. But again, this whole group is an ester. And since we're looking at a strong reducing agent, we will be able to convert this carbonyl to an alcohol. So we're going to have 1, 2, 3, 4. So coming off carbon 1, we're going to have an alcohol. And coming off carbon 4, we're going to have an alcohol, because this alcohol here is coming from our ester, and this alcohol here is going to be coming from our aldehyde. So you can kind of look at these comparatively and see that in both cases, right, so looking at with sodium borohydride and looking at lithium aluminum hydride, so when we look at lithium aluminum hydride, we have the capabilities of reducing that ester. I should show you here also that, so lithium aluminum hydride is the first step. This is typically done in like diethyl ether. THF would work also here. And then you need some acidic conditions, so you can just show it as H3O plus or H plus, either of those will work. So those are typically the reaction conditions when you're doing reduction with lithium aluminum hydride. So it's a little bit different than the media when you're using sodium borohydride. But again, you have either diethyl ether or THF, and then you just need some acidic conditions. So looking at these reactions, you should be able to reduce, right, with either sodium borohydride or lithium aluminum hydride. You should understand what type of products would form, what's the differences between the two. So again, lithium aluminum hydride can just reduce carboxylic acids and esters along with aldehydes and ketones, whereas sodium borohydride cannot do that. And then you want to kind of keep in your mind freshly the ozone. So looking at chapter 8, think of what ozone can do when we're looking at oxidation reactions. So this is actually it for chapter 10. So chapter 10 is not too bad. A lot of the stuff, like I said last time, are things that you have seen before. And then there's really just the new reactions with the Grignard reagents and then these reducing agents. So those are really the two main points in chapter 10. And again, work on problems, do my problems, do Professor Madrick's, do Professor Rosenstein's, and then make sure you reach out with any questions. You will not have a quiz until chapter 10 and chapter 11 are completed. I hope you all are doing well, and you may hear my kids screaming right now. So it's the perfect time to end. Have a great day.